Thanks for clicking on this video. Today we're going to be working with binomial probability. If you want to follow along, the links to the companion worksheet are in the description below. Also, don't forget to click that subscribe button to stay up to date on all the videos we have coming out from the channel. So this is an application of the binomial theorem where we have two outcomes, but they may not have an equal 50-50 shot. Now, how do we model this? So here it says we have a fair coin. So when we flip a coin, we have two options. We have either heads or tails. And in a fair coin, each of them has a 0.5 chance of happening. Okay. But we flip this 10 times. So this is where the binomial theorem comes into play because we have two outcomes, h plus t raised to the 10th power. All right. Now, we don't actually have to expand this out completely because all we care about is the probability that it lands heads exactly 5 times. So we only care about the term where it's going to land heads 5 times. Well, let's think about that. If it lands heads 5 times, that means it's going to land tails 5 times. So what's going to be the coefficient out front? Well, that's going to be 10 factorial over 5 factorial times 5 factorial. So if I get out my calculator, we can calculate 10 factorial divided by 5 factorial, and we'll do that twice. And we get 252. Now in place of h, we plug in the probability. Since this is a fair coin, it's 0.5 to the 5th. Same for tails, 0.5 to the 5th. So we're going to take 252 and multiply 0.5 to the 5th, and we're going to multiply 0.5 to the 5th. And so we get 0.246 as our probability. So that is our probability that it lands heads exactly 5 times. Now let's look ahead to the next one. Same situation. We have a fair coin, flipping it 10 times, but now we're saying what's the probability that it lands heads 8 or more times? All right, so here we've got multiple situations. Could land heads 8 times, which means it lands tails twice. It lands heads 9 times, which means it lands tails once. Or it lands heads 10 times, it lands tails 0. So what are the coefficients? Well, it's going to be 10 factorial over 8 factorial 2 factorial. Here it's going to be 10 factorial over 9 factorial times 1 factorial. And here it's going to be 10 factorial over 10 factorial times 0 factorial. So this one, this coefficient here is going to be 45. And then we plug in 0.5 to the 8th and 0.5 squared. And to that we add this outcome because it's not just exactly 8 heads, but or 9 heads or 10 heads. All right, so this one is going to be 10 times 0.5 to the 9th times 0.5 to the 1. And then finally, 10 factorial over 10 factorial is just 1 times 0.5 to the 10th. Now, one thing to notice is that these three are all the same thing. We're just multiplying 0.5 10 times. So all we have to do is just add up these coefficients. 45 plus 10 is 55, plus 1 more is 56, times 0.5 to the 10th. So 56 times 0.5 to the 10th power. And we get 0.0547. 0.547. So there's our probability that it lands 8 or more times. All right. So on to the next page. Now we're talking about a rigged coin. So now we don't have a 50-50 chance of it landing heads or tails. Here it says it lands heads 60% of the time. And it lands tails 40% of the time. And that's important. Now here we're flipping it 6 times. So that means if we were to expand it, this would be h plus t to the 6th power. Now here we want to know what is the probability that it lands heads exactly 3 times out of 6. It's heads exactly 3 times. So that means that h is going to be to the 3rd, so t is going to be to the 3rd. Because if it lands heads 3 times out of 6, then it has to land tails 3 times out of 6. And so our coefficient, the number of ways this can happen, is 6 factorial over 3 factorial 3 factorial. So we take 6 factorial divided by 3 factorial times 3 factorial. And I put that in parentheses so my calculator understands. All right, so we have 20. Now, in for heads, we put 0.6 cubed. And in for tails, we put 0.4 cubed. So I take 20 times 0.6 to the 3rd times 0.4 to the 3rd. And so we get an answer of 0.276 as our probability. Now for the 4th one, similar, except that now we're talking about more than just one outcome. 3 or fewer. All right, so let's count this out. So it lands heads 3 times. It lands heads 2 times. It lands heads once. Or it lands heads 0 times. Okay. Now we already figured out that this was 20. And so the probability was what we just found, 0.276. But we still have to figure out these 3. So this is going to be 6 factorial over 2 factorial times 4 factorial. This is going to be 6 factorial over 1 factorial times 5 factorial. And then this is going to be 6 factorial over 0 factorial times 6 factorial. All right. So this is going to be 15. And in place of h, we put 0.6 squared times t, which is 0.4. And to that we add 6 times 0.6 times 0.4. Whoops, that should be to the 4th right there. This should be 0.4 to the 5th. And then finally, 1 times 0.6 to the 0 times 0.4 to the 6th. Now, unfortunately here we can't combine terms that will mesh like they did in number 2 because each of these are different. So we have to compute each of these one by one. All right, so 15 times 0.6 squared times 0.4 to the 4th. So we have 0.138. And so now we have 6 times 0.6 times 0.4 to the 5th. So that's 0.037. And then finally, we have 0.4 to the 6th, which is 0.004. All right, 0.004 plus 0.037 plus 0.138 plus 0.276. So we add these probabilities all together, and we get 0.455. And so this counts 3 heads, 2 heads, 1 heads, or no heads. And then on number 5, now it asks, what's the probability that the coin never lands all heads or all tails? All right. Now we could count out all the probabilities of things we do want, but I'm going to show you a different way to do this one. Count what we don't want. So all heads, what's that? Well, that's going to be h to the 6th, t to the 0. And there's only one way that could happen. What about all tails? 1 t to the 6th, h to the 0. There's only one way that could happen. So this is going to be 0.6 to the 6th. And this is going to be 0.4 to the 4, because anything to the 0 power, whether it's t or h, is just going to be 1. So let's calculate those two terms. Again, these are the parts we don't want to count. So 0.047, and this is 0.004. Now, since this is the parts we don't want, to get what we do want, we subtract them from 1. So subtract 0.047 and subtract 0.004. So 1 minus 0.047 minus 0.004. Whoops, that should be a 4, not a 1. So we get for this one 0.949 as our answer. Now on the last page, now we're not talking about coins, now we're talking about multiple choice questions on a quiz. And some people think, well, that's not binomial. Well, sure it is. You have two outcomes. You could either guess correct or incorrect. Now, if you're just guessing purely randomly, what are your chances of guessing correct? Well, your chance of guessing correct is 1 out of 4, because there's 4 different answers to choose from. And so your chances of getting an incorrect answer is 3 out of 4. So this question is, what's the probability of passing the quiz by answering 4 or more questions correct by guessing randomly? And so we have to answer either 4 right or 5 right. So listing this out, this is going to be c to the 4th, I to the 1, or c to the 5, I to the 0. And so our coefficients, this is going to be 5 factorial over 5 factorial times 0 factorial. Over here, this is going to be 5 factorial over 4 factorial times 1 factorial. So when we calculate this, we get 5. Now we plug in 1/4 for our correct chance, and then 3/4 for guessing incorrectly. This coefficient is just 1 when we calculate it, because there's only one way of answering 5 questions correctly. But there are 5 ways of answering 4 right and 1 wrong. The first one, the second, the third, the fourth, or the 5th could be wrong. So plug in 1/4 to the 5th. So now in our calculator, we take 5 times 1/4 to the 4th times 3/4 to the 1st plus 1/4 to the 5th power. And so added all together, we get 0.0156 as our probability. Now, for our last question, now we have talking about a plane engine with 1,000 parts. And each part has a 0.1% probability of failure. So that means that either an engine part will fail or it will work. And so if it's a 0.1% probability, that means it's 0.001, whereas the probability it works is 0.999. Now it asks, what's the probability that one or more parts fails? And that's a very long answer, because that means if we expanded this binomial, w plus f, to the 1,000. However, let's think about this for a second. The first term is going to be w to the 1,000, meaning that all 1,000 parts work. What's the second term? 1,000 plus w, 1,000 times w to the 999 f to the 1. ... Now what do we want? We want all of this. We want all of these chances added together. Well, that means that this is what we don't want. And so similarly to number 5, we can figure out what we don't want and subtract it from 1. So we plug in 0.999 to the 1,000 power. So this is the chance that every single part will work. And so we get 0.368. And so that's the probability that all 1,000 parts work. And so, to figure out that one or more parts fails, we take 1 minus 0.368, and we get an answer of 0.632. And there's our answer. Thanks for watching, everyone. If you liked the video, please give it a thumbs up. If you have suggestions or problems you want to see worked out, type a comment below. To support the channel, click the Patreon link to help keep this going. Thanks so much for watching. And remember, the best way to understand something is to do it.